All right, so let me introduce our speaker. Our speaker is Emory Wellman, and Emory is a fourth-year PhD candidate in the Fisheries and Aquatic Sciences program at U.S. School of Forest, Fish, and Geomatics Sciences. That's a mouthful. Emory actually received a bachelor's degree in government from Georgetown University. And after that degree, she worked in environmental policy for a few years when she decided that she was really more interested in field research. So she took a little bit of a pivot and began working in field work at the University of Massachusetts, at Dauphin Island Sea Lab, and the Institute of Marine Sciences at the University of Chapel Hill. Then she went back to school and graduated with a master's degree from East Carolina in 2021, where she examined alternative oyster reef substrates and their impacts on salt marsh shorelines. She came to UF in 2021 to start her PhD and has continued working on oyster reefs and salt marshes, and that's the work that she's going to talk to us about today. So thank you so much, Emory, and I will turn it over to you.
Thank you, Laura. Let's see if I can get this. Okay, how does that look? Good, okay. Please let me know if it gets bad in any way. All right. Good afternoon, everyone, and thank you for tuning in today. As Laura said, my name is Emory, and I'm very excited to talk about one of my PhD projects in which I'm examining the influence of wave energy on Big Bend oyster habitats. I do want to say upfront that this project is very much still in progress, so unfortunately, I'm not going to be presenting tidy, complete findings, but I have some preliminary results, and I hope that the methods and my approach more generally will foster some good conversation. To set the scene, I'm not going to speak all that much about intertidal oyster reefs in the Big Bend because I am sure this audience is already well aware of their economic and ecological importance to this region. Very briefly, intertidal oysters in this area are an extremely valuable target for harvest and perform critical ecosystem functions like water quality improvement and habitat provision. Additionally, intertidal oyster bars perform a service unique to this area. Essentially, oyster habitats which form parallel to the shoreline help to trap fresh water as it runs into the ocean, which maintains a brackish habitat both to the benefit of their own persistence, but to the benefit of other estuarine fauna as well. Unfortunately, many of these critical functions are under threat. So over the past 29 years, estimates indicate that about 66% of oyster reef area has been lost in the Big Bend, which mirrors losses that are happening in shellfish habitats around the globe. A recent report commissioned by FWC confirmed that a major portion of intertidal reefs in the overall study area, which means the Sewanee Sound region, have been lost in recent decades. So researchers, including many at UF, have pointed to predation, harvest, disease, and changes in the timing and quantity of freshwater flow as potential drivers behind these losses. For example, decreased riverine flow increases the salinity of estuarine waters, which can then facilitate an increase in disease prevalence and the abundance of predators like the oyster drill, which is shown in part A of this photo, and their egg sacs in part B. Now, an additional stressor which has received less attention than the ones mentioned on the previous slide is wave energy. Obviously, wind and boat waves are common occurrences around intertidal oyster habitats in the Big Bend, and wave energy is frequently mentioned as a factor which may exacerbate reef decline, but not in any particular detail. Waves and strong hydrodynamic forces can disturb and move sediment and oyster shells, which may also impact the live oysters attached to the shells. For example, in the Indian River Lagoon, boat wakes have been found to create so-called dead margins, or these mounds of shell, which are washed up on the reef above the waterline and subsequently experience reduced survival of juvenile oysters. One example of an attempt to quantify wave energy and its impact on oyster habitats actually comes from North Carolina. There, researchers used hindcasted models of wind and waves to estimate that reef formation typically did not occur above energies of about 500 joules per square meter. However, it's important to note that no wave data were actually collected at any of their study sites, which is unfortunately not uncommon due to the high cost of typical wave pressure gauges. So essentially, coastal ecologists have for a while been aware that oyster habitats impact waves by decreasing their height and attenuating their energy, but I started wondering whether the relationship goes the other way, meaning can waves impact the form and function of an oyster habitat? For example, if waves and boat wakes can cause shells to move, what about larger forms of oyster growth? So this is when I started my obsession with what I call oyster clumps. Other people refer to them as clusters, and the role that wave energy might play in both their formation and their fate. This photo is from Corrigan's Reef in Cedar Key and shows a more contiguous reef surrounded by clumps. The more contiguous reef is in the background with some marsh vegetation. And I don't have time to get into it this afternoon, but in one of my other dissertation chapters, I've shown that clumps can move more than 50 meters when set out on intertidal bars like this one. So wave energy certainly has the ability to play a role in shaping these habitats. I therefore started wondering whether there's a relationship between oyster habitat contiguity, or its form, and wave energy. Obviously, oyster habitats are not all identical, but rather exist along what I consider a spectrum of contiguity. So the really classic reefs, like the photo on the left, are those which have essentially uniform, contiguous live oyster coverage. Then as oyster biomass declines, as in the middle photo, so does contiguity, and you end up with a habitat dominated by clumps, which are separated by sediment or shell hash. And then the least contiguous version is the photo on the right, which has only remnant oysters and otherwise is all sediment or shell hash. As I'm sure everyone is painfully aware, as oyster habitats and marine habitats more generally become less contiguous, monitoring them becomes more challenging. And habitats like those in the middle and on the right may not be included in mapping and inventory efforts at all. And this is obviously a problem because even if these habitats look different or they may have less biomass than the classic reef, they are still living oysters which perform valuable functions and contribute to the Big Bend ecosystem. So before getting into my research, I want to quickly highlight the excellent work which has already been done to identify and inventory oysters in this region. The researchers within the Oyster Integrated Mapping and Monitoring Program have developed a statewide oyster map for Florida, and they publish regional reports describing their mapping techniques and some findings about how habitats have trended through the course of their monitoring. I've included a few excerpts here, which highlight the issue of contiguity that I discussed in the previous slides. Namely, the fact that these oyster habitats are very diverse in their appearance and their form, and that it is difficult in standardized large-scale monitoring to rigorously document living versus non-living portions of oyster reefs. So essentially, distinguishing between living oysters and areas of that sediment and the culch that I showed in my previous photos. So after reading these reports, I started thinking about ways to address these challenges and build on WIMP's existing work. Specifically, the needs to me seems to be as follows. There is a need for additional management relevant information, including that which describes oyster biomass and habitat configuration at these inventoried oyster sites. And second, to maximize the utility of this information, the methods used should be somewhat easy and repeatable. So these are the concerns which I kept in the forefront of my mind as I designed this study. And when I started thinking about increasing the scale and frequency of data collection, this line of thought led me pretty quickly towards unmanned aircraft systems, better known as drones. Typically, the footprint and the elevation of oyster reefs are mapped by physically walking over and around a reef with a high-resolution GPS unit. As I make very clear in this photo, in which I am mapping an oyster reef in North Carolina a few years ago, this method is not too easy and is limited by a lot of concerns like access, site size, and the potential repeatability of the method. I'm obviously not the first person to think of using drones, but the increasing feasibility in their costs and usage means that they're becoming a valuable tool even for ecologists who tend to shy away from complex technology, very much like me. This field is evolving really quickly. New software is becoming available and workflows are becoming more streamlined and more understandable to kind of a lay scientist. The most important thing to know is that using a technique called structure from motion, researchers can collect typical 2D images but get 3D products. Essentially, by taking several overlapping photos of the same area from different angles, you can produce extremely detailed images, which are called orthomosaics, and elevation models, which are digital surface or digital elevation models. And I won't get too into the weeds here, but briefly, terrific progress is being made using drones to map and to better understand oyster reefs. On the right, I'm showing the results from a study which compared the accuracy of drone surveys with the traditional surveys which are done on foot. And encouragingly, the authors found that these two approaches generally provide equivalent results for mapping these reefs. In China, drone analyses have allowed researchers to specifically identify reefs which are experiencing degradation based on their ability to analyze and quantify fragmentation from their drone images, which otherwise wouldn't have been possible using an on-the-ground survey. And lastly, several studies have been able to use repeated drone flights to track changes in the amount of oysters present at a site and the size of a reef, which is really encouraging for the potential use of this technique for monitoring. So bringing all of those many threads together, my research question is, how do oyster density and size class structure differ among habitats which are subjected to different levels of wave energy? This study took the form of a survey in which I collected data at 20 oyster sites in and around Cedar Key, Florida. The key data that I collected for this study were in situ site-specific wave energy information, RGB drone imagery of each site, and information about the oysters at each site. In May 2023, I identified 20 oyster habitats which varied in their hypothesized exposure to wave energy. And I took my best guess at wave exposure based on fetch, which is the unobstructed distance over which a wind wave can travel. So larger fetch tends to mean that a site will be experiencing more wave energy than one with a really small fetch. I also wanted to vary the degree of freshwater influence at these sites with the presumption, and I mean, it is just true, that the fact that water around the sites farther from the Suwannee River would be more saline than the water around sites closer to it. So I therefore chose 10 sites in the Shellmound region, which is relatively near the mouth of the Suwannee, and 10 sites farther south in and around Cedar Key. I also tried to vary the degree to which these sites had contiguous live oyster cover. So in the top photo, you can see that the oysters at this site, site 12 in Shellmound, are in discrete clumps separated by sediment, whereas those at the southern site are forming a more contiguous reef. As I mentioned before, standard wave pressure sensors typically come with a price tag of about $3,000, which means that it is financially prohibitive for many researchers to collect wave data. The good news is that some researchers at Mississippi State University designed a DIY wave gauge, which performs as well as the industry standard at a fraction of the cost. So I built many wave gauges following this design, and we completed 3 2-week deployments at each of my sites between July 2023 and June 2024. Very basically, these gauges collect 10 water pressure measurements per second, so at a frequency of 10 hertz, which we can then convert to wave height and then to wave energy through the wonders of MATLAB software. Next, I collected drone imagery at each site using an Anafi USA drone. Each of these flights occurred at a low altitude of 25 meters. And as I mentioned before, the degree to which the path of your drone overlaps itself is what allows the use of structure for motion analysis. So I purposefully flew with very high overlaps, and I used the drone's native RGB camera. So I didn't add any special payload. At each site, I also installed and surveyed 3 ground control points prior to flying, which essentially improves the accuracy of the final products. And then obviously oysters are quite small in the grand scheme of an aerial image. So I targeted a very small ground sampling distance, which is essentially the amount of ground area that is represented in a pixel in the final product. So a small GSD means high detail, meaning a ground sampling distance of 0.7 centimeters per pixel was really good for my purposes. So this is an example of an orthomosaic, which I assembled from a flight I did over one of the sites at Shell Mound. They're kind of hard to see, but the little black and white dots are the ground control points. And you can see that the flight also captured surrounding mudflat and an adjacent oyster reef, which also has some marsh vegetation. Lastly, following drone flights, I collected samples from each class of matter which existed at the habitat, meaning some combination of oyster, shell, sand, or mud. My goal here was to try to account for potential oyster biomass in every substrate type within a given oyster habitat, rather than presuming that all of the oysters are concentrated kind of only within the oyster clumps and aggregations. We counted and measured every oyster in these samples, giving us size, class, and density data. And just to elaborate a little more on the idea of the class, here I have zoomed into the orthomosaic I just showed you to better visualize this. So at this site, there were 3 classes: oyster, shell hash, and mud. Oysters in the image are pretty obvious. They're irregularly shaped and they tend to stand out from the background. Shell hash is typically pretty bright and it has a little bit of texture, but not as much as the oysters. And then mud tends to have essentially no texture and is, unsurprisingly, a pretty uniform brown color. And before wrapping up the methods, I want to quickly talk about the way in which I classify my images, or how I pull out the detail of the shell hash versus the mud versus the oyster. So typically classification, oh no, okay, sorry, pretend you didn't see that. Typically classification in remote sensing is pixel-based, meaning software goes pixel by pixel and analyzes how the spectral information in each one compares to its neighbor. However, recently there has been sort of a movement towards what's called object-based image analysis, or OBIA, which, as the name implies, compares entire objects rather than pixels in classification. So a key component of OBIA is the segmentation step, in which the software groups pixels into objects from which classification then proceeds. So on the right, I show a subset of one of my orthomosaics before and after segmentation. You can see that in this step, the software has drawn little perimeters around patches of oysters and started to kind of do the work of separating oyster from shell hash material. An important attribute of OBIA is that, again, to folks like me who don't spend a lot of our time around complex software, it works a lot more like a human mind, because obviously we can conceive of things better when it's an object with a meaningful context versus an individual pixel. And some researchers in my department have done really incredible work, also in the Big Bend, advancing the field of obia. My collaborator, Dr. Michael Espriella, and his PhD advisor, Dr. Vince LaCours, used obia to classify a large flight that they did in Little Trout Creek, which the results are pictured here. I like to think of my work as essentially a smaller version of what Michael did. So while in this figure, he's classifying different habitat types with terrain landscape, I'm classifying different types of substrate within a single type of habitat, if that makes sense. Very, very briefly, I wanted to show my workflow for analyzing my drone data. Unfortunately, it involves 4 different softwares to assemble, prepare, and analyze the orthomosaics and the DSMs from my flights, with the obia portion specifically being performed by eCognition software. Okay, so as I mentioned in my intro, I am still deep into analysis. So the best I can do today are some preliminary results. I'm going to focus specifically on sites 8, 9, and 10, which are adjacent to the Cedar Key Airport, as shown in this Google Earth snapshot. My rationale for choosing these sites was, again, based on exposure to wave energy, with my logic being that site 8 would be most exposed, site 9 medium exposed, and site 10 quite sheltered if we assume that the majority of wind waves are coming from the west. And just to provide a sense of scale, site 8 and 10 are 293-ish meters from one another as the crow flies. All right, so I have generated orthomosaics for all 3 sites, and I've overlain them on the Google Earth screenshot, which is why it looks a little funky. I have also finished the obia for sites 9 and 10 and generated classified landscapes. And unfortunately, I made the grave mistake of telling some people that I planned to highlight sites 8 through 10, which of course meant that I jinxed myself, and the obia for site 8 has been hands down the most challenging one yet, and a new classification is running next door as we speak. So while the following oyster and wave data do indeed apply to site 8, we are very briefly going to entertain the notion that the imagery that we're looking at is site 8, when in fact it is site 6 in disguise. So just join me in briefly suspending disbelief. I'm using site 6 as a visual stand-in because, as you can see, both sites are dominated by non-oyster sediment and shell hash, with a relatively small amount of their area made up of oysters, which show up as dark speckles. So what I'm showing in this slide and in the next 2 slides is the raw orthomosaic on the left, which is what comes out of the Pix4D software. Then the cropped version, which I prepare in ArcGIS in the middle. And then finally, the classified image, which is produced by obia, where blue represents oyster, yellow represents sand or mud, and green represents shell hash. So this color scheme will be true for all the following images. And back to our regularly scheduled programming, these are the same products from site 9, so raw, cropped, and classified. And then from site 10, so same thing, raw, cropped, classified. And then here are the classified images from site 6, 9, and 10 lined up next to one another. And I know that the colors can be hard to look at because they're so bright, but if you can, try to focus only on the blue, which are the oysters. So hopefully, if nothing else, you can see that the amount of blue is increasing as you move away from site 6 or 8, which was the really sediment-based, or excuse me, sediment-dominated site. And I will say I do expect that site 8 will look similar based on that orthomosaic I showed you. Okay, so forget about site 6. It served its purpose. Now we're truly back at site 8. I apologize for the last minute change of arrangement here. So moving to the oysters, here I have pulled the data for spat and adult oysters averaged their densities across samples. So this is obviously extremely preliminary and there are no statistics here, but there are some interesting kind of early impressions. First, the one I noticed is that mud is hosting essentially no oysters at these sites. So to me, this means it could actually be really important for folks who are doing monitoring to distinguish between the so-called no oyster habitat classes, because shell compared to mud is actually hosting quite a few. So it may be inaccurate to assume that shell and mud perform the same function or lack thereof within an oyster habitat. I also found it interesting that at these sites, the density of adult oysters increases as you move inland and into a more sheltered area, but the density of spat actually follows the opposite trend. So this is very much a kind of early impression, which I could 100% be proven wrong, but I'm wondering if this is because larvae held in the water flowing in from the Gulf are kind of settling out once they hit the friction and the obstacle provided by Site 8, but then they aren't surviving to adulthood at this site because, drumroll, of the fact that the wave energy levels reported here in joules per meter are quite a bit higher at Site 8 than they are at the other two sites, with the wave energy logged at Site 10 is very close to zero. So together, this information is an early encouraging indication that maybe my theory about kind of decreasing wave exposure along this gradient is indeed being borne out in the data. Okay, so while we're talking about the wave data, this is specifically something to which I will be devoting a lot of time because there are many scientifically valid ways to analyze wave data, and it's a matter of finding the one which is most appropriate for a project. What I'm showing here are data from Site 9. I'm sorry, this is so small, but essentially we have wave energy on the y-axis, wind gust on the x-axis, and the data are binned by the 16 cardinal wind directions. So my collaborators who have collected wave data at Corrigan's Reef and Gulf-facing islands around Cedar Key have had really good luck with this approach, where they actually get high R-squareds between a given wind direction and a wave metric, which actually allows them to construct a predictive model. However, with some of my wave energy values being as low as you've just seen, I'm not convinced that I can pull this off. I don't know if the wind will ever really correlate that nicely with such small values. So there will definitely be some brainstorming before I can kind of get a true hold on my wave data. And then once I have finished OBIA and obtained my classified landscapes, the final step will be loading them into R and analyzing them using the landscape metrics package. If anyone is familiar with FragStats, this is essentially designed to be the R version of that program. I grabbed this image from the package documentation because it demonstrates a classified landscape, much like mine, which is what you use as input. From there, you can either analyze the landscape as a whole or the individual classes, so kind of the different colors, or individual patches. So it's a really powerful tool, and it has a huge range of metrics, including area, shape, compactness, and the degree to which a class or a landscape is clumpy or aggregated, all of which will be really important analyses for me. And additionally, simply knowing the area of each class will be particularly great because at that point, I'll be able to scale up my oyster data from the sample size to the landscape, which gives me a very rough but kind of baseline initial idea of how many oysters are present at a site. So I have shown only a small subset of my data, and I'm sure it's pretty obvious that I have a lot of work remaining on this project. This includes the wave data, the OBIA analyses, the landscape metrics analyses, and then hopefully some statistics which can provide a little information about the relationship between these oyster habitats and the wave energy they experience. And on that note, it is very important to say that this is a survey and not a manipulative study. So at best, I will be showing correlation rather than causation. Meaning, I can in no way say that a given level of wave energy produces a given oyster biomass outcome, since obviously oysters do not respond to environmental drivers on the same timescale that waves hit a shoreline. And as I described in the introduction, oysters are responding to dozens of other drivers in their habitat at a given time. So attributing my results purely to wave energy would be severe oversimplification. However, you need to start somewhere. So I see this study as being an important first step to investigate whether this sort of approach will even work and whether it can be refined going forward. And to make a quick note about my workflow, unfortunately, it is not as accessible as it could be, given that I am relying on an expensive drone and 3 proprietary software programs, all of which can be barriers to entry. However, from speaking with collaborators, it does seem that open source workflows using R and QGIS and the like are also developing rapidly. So I hope that this approach will become more accessible over time. It's also important to note that although the OBIA approach does have a learning curve, which I am very much still climbing, it does fulfill one of my big goals, which is that it is repeatable. Meaning once you have essentially tuned your workflow and your parameters for a given site, when you get new imagery, it's pretty easy to just press play on the workflow and check how change has happened over time. This is obviously a critical part of monitoring and managing systems like oyster reefs because it's impossible to plan actions like restoration without a firm understanding of whether a habitat has been changing and by how much. So I'm trying to finish a degree here in the relatively near future, but given more time and funding, I think testing the repeatability of this sort of approach is a really important next step. And then lastly, one cool thing about this project is that I have quote unquote found some quote unquote new oysters. This image is from a site west of Shellmound, which I learned is not actually included in the WIMP statewide oyster map, which is pretty cool. So all of the dots and gray patches in the yellow rectangle are oysters, all of which right now are currently kind of not being incorporated in this statewide inventory. So again, this will be for some future researcher to tackle, but I'm wondering if drone imagery is potentially a useful tool here in terms of kind of seeking out and ground truthing oyster habitats which aren't being tracked. And I very much plan at the end of this project to kind of check my sites against the statewide oyster map. And if possible, I want to make sure that these new ones have the opportunity to be incorporated. Okay, I will leave it there and would like to end by thanking my many incredible collaborators. I put myself almost entirely out of my comfort zone with this project, and I'm making sense of my data only because of the time and energy and kindness of the people listed here. I am extremely grateful to Florida Sea Grant for funding this project through their Graduate Student Coastal and Ocean Fellowship. And while I've listed some specific NCBS staff and researchers here, I also want to thank everyone at NCBS more generally for being such a welcoming and supportive community as I worked on this project. So I know this was a lot of information delivered quickly, so I've also included my email in case you have additional questions or comments after the seminar ends.
Thank you so much, Emory. But folks are probably busy filling out the poll a little bit, but we have plenty of time for questions. You're welcome to put those in the chat, or if you'd like to unmute yourself and ask a question, um, you're welcome to. And there actually already is a question in the chat. And where did you get the fetch data?
From my brain and my best guess. Essentially, you can, there are ways to actually make a wind wave model on Google Earth that you essentially draw out vectors and you can measure the distance on each kind of vector to the nearest obstruction, which may feasibly knock down some of the energy. But I don't think I have a good image, but some of these sites, like the shell mound sites that I showed, there's just not really anything between them and the Gulf. So that's kind of it was a best guess scenario because I didn't really have the time or ability to do a preliminary wave gauge deployment, which would have been the best way to do it. But honestly, I don't think that's that bad because, for example, in my master's, I completely just assumed that one of my sites was lower wave energy than the other just because it did have kind of like it was in a tidal creek versus on a facing shoreline. So this is how people, I mean, without access to these actual instruments, this is kind of the best way to make a guess at that. So, so yeah, it was kind of vibes based. I think Annie had her hand up.
Emory, thank you so much for sharing a bit about your research in detail and a very good talk. I can't believe we haven't had this conversation together about those clumps or clusters. I'm so excited that it's been being investigated. It's one of the first observations I made here in Cedar Key because I haven't quite seen that type of structural complexity like in that morphology in other oyster reefs. It's so pronounced as little balls of oysters. While you were thinking about what to study and what creates that, before you selected waves, did biotic control come into play? Because my thought immediately went to crown conch, but I'm biased because I've done studies with crown conch, and I was thinking that the balls were made because the ones on the sides aren't dense enough where they can get their mantle over and open the oysters and kill them. But once they get to that high cluster, which ends up always being a ball for some reason, which I didn't have an explanation for that, you know, then the crown conch can't get it. So I babbled to repeat while you were thinking and before you picked wave action is the reason. Did you think about biotic controls and do any testing there?
No, but I think I've talked with Joe and Mark and other Joe about this quite a bit, is that I think the crown conch are something that absolutely need to be considered because I'll be honest, I arrived at this sort of idea in a very early 1900s naturalist way of I just saw clumps rocking back and forth in the waves and I thought, oh, that's kind of cool. And that image I showed of the Cedar Key reef that's kind of like producing these clumps, if you, and I've done this, if you go over and you kind of tap the edge with your foot, the clump just falls off. So my brain went to, okay, well, a wave could do that. But I think you're totally right. I'm sure it's some sort of synergistic thing of if the conch is weakening at first, then absolutely. But yeah, and that's what I should have made this point as well, is that I don't see wave energy being the cause for reef degradation or reef decline. I do think it's a situation that something else has happened so that these reefs aren't in their top state. And then wave energy is kind of able to exacerbate the problem. So the conch could totally be that kind of like proximal cause.
Thank you, Emory.
Yeah, let's design a project. As I just said, I need to finish my degree.
In our free time, yes. Yeah, okay.
Thanks, Emory. I love projects that start off with really astute observations. So I appreciate that. We have a couple questions in the chat about hurricanes. Not surprising after this year. Have you been back to your site since the hurricanes this past fall? Any changes that you've noticed? And also how do post-hurricane studies, extreme wind events impact these studies?
So I've been back to a few of the sites, but unfortunately have not flown them, which again, honestly, I think drone imagery is so much more powerful because I walked around these sites several times and I thought I knew what they looked like. And this is very obvious, but it's not until you see it from above that you really understand what's going on. In fact, I lost a wave gauge and I was convinced it was gone for all time. When I was working on an image yesterday, I found it. So it's still there. I just couldn't see it on the ground. Anyways, no, I have not been back. And unfortunately, that is sort of a funding shortfall. But I think along the list of the many other studies that I think need to be done, that is absolutely one. And it might not be too late. I feel like I could go back. There are a few which are easier to get to than others. So that's not a bad idea to maybe at least target some of the like the ones that are closer to shore and are kayak accessible versus a whole airboat ordeal. But that's a good question. That's definitely a shortfall. And then how to host post-hurricane studies. I don't quite understand. I'm just going to assume this means how do extreme wind events impact these studies. And I think that it depends, because we've sort of seen this already with Adalia, is that, or what's an Adalia is a different one. But essentially, oysters, I think, are less impacted when a storm surge is higher, because at a certain point, water is kind of an insulator and they're almost completely protected once the actual wave action and the scour can't reach them. So, and I found this in my master's too, that if a site is completely inundated, it's actually probably going to be fine. It's when the water level is such that the waves can kind of get direct access at it. And that's also very true of studies of marsh scarp erosion as well. So definitely has an impact. It depends on the storm surge and kind of the tidal stage when the hurricane is hitting, that sort of thing. And then I think Stephen had the next.
That's right.
Yeah, hi, Emory. That was great. Thank you. So your pressure gauge data, have you, I don't know how much detail you've gone into with it. Well, let me back up. So early on, you were talking about boat wakes and wind-driven waves. Are you able to have some idea of the relative impact of those two wave sources?
Unfortunately not, with the way that this software works, which I think Mark and Alex who are the wave experts, can cut me off if I'm wrong. But my understanding is that unfortunately you can't pull out individual waves, or if you can, it's very hard. Whereas in some of the commercial sensors, you can actually analyze wave by wave, which does let you kind of compare the relative importance and power. Whereas these are very much kind of, it will log the absolute pressure, and that's sort of what you get. So that is an important thing I need to kind of make sure to include, is that there are most certainly boat wakes in some of this data, and I can make a best guess at which sites are going to be frequented more by boats versus ones that aren't. But that will, again, be another future study, is trying to parse that out, because you can do some analyses, like boat wakes do have some kind of hallmark characteristics that you can pull them out if you know what you're looking for. But unfortunately, I'm not sure that my data set is going to allow that detail.
If you have that 10 hertz sampling, and it's continuous over a long period of time, then yeah, you have the data. That's all you need.
Okay, well then I'll talk to you afterwards.
We've done that kind of work here in Tampa Bay. So we have plenty of software to pull out boat wakes if you're interested.
Oh, all right. You know, I was kind of hoping that someone would see that horrible plot and just feel bad for me and offer to help. So maybe you're my my deliverer.
We'll do what we can. Thank you.
Thank you.
We have a couple more questions in the chat and a couple minutes to answer those. The first is, have you noticed if there's any correlation between the formation of clusters and the longer, more contiguous reefs in different sediment types, or is it purely a longevity of buildup/development factor?
Ooh. So this is at best a guess. I'll be honest, I haven't thought much about this. But again, something else I didn't want to go into for the sake of time was that in early discussions with my committee about the oyster clumps, I started by almost unilaterally referring to them as I described earlier, as a symptom of decline, of they are the product of a reef that is falling apart. But then we had a lot of good discussions about how that's probably, or not probably, is definitely not true, because an oyster clump can kind of arrive at its existence either through a top-down or a bottom-up, what I call top-down or bottom-up pathway. So the reef that's falling apart and is kind of crumbling into clumps is the top-down. But clumps are how reefs start in a happy, self-sustaining reef situation. So it could be that if you see a given clump out in Cedar Key, it may be the fact that it was an oyster that is now recruiting and is growing, and it's going to merge with a neighboring clump. So I actually have found that I'm not sure. Sediment, I think, does serve as an indicator because of it being a proxy for wave energy. So again, my best guess is that you're going to see the bottom-up clump formation in muckier sediment, with the muckier sediment being an indication of less wave energy. And that's kind of the best I can do. Sorry, I'm not sure if that answered the question at all. But like in my set of 3 photos in which I discussed the contiguity, the middle photo that was clumps separated from one another, that's like very muddy substrate in between them. So I think that, and that site is very sheltered. It's behind 2 islands. So I think that's a case where it's a bottom up, and given enough time, hopefully that would become a reef.
Oh,
sorry, that was a really good question. I'm not sure I answered it.
We have another question in the chat, and that is, can you tell if the degree of clumpiness impacts the habitat behind the oysters? Do oyster clumps protect the marsh from wave energy/erosion?
So I tried to answer this in my 3rd chapter, in which we put clumps of oysters into a wave flume, which is essentially a tank in which you can fine-tune specifically all the wave characteristics, the period, the height, the energy. And I really wanted to figure out if, so essentially the focal clumps in the flume had sensors on them. And we had a bunch of cement casted clump mimics, which a different student used for his PhD. And I lined up a bunch of the kind of mimics in front of the focal 4 with the sensors. And I was hoping to see essentially some some information about, oh, if you put a barrier there, they knock down a bunch of the wave energy, the clump with the sensor is going to move much less. And I think, I haven't looked at this data in a while, but I think the reverse actually happened. So that's when we really need an engineer to maybe parse the fluid dynamics, or maybe the fact that the clumps can form a channel. So maybe they're actually directing wave energy in a kind of enhanced form towards the focal clump. But from my sites, which are predominantly clumps interspersed with marsh, the marsh seems to grow out into the clumps. It pops up because it grows, Spartina grows clonally, so it's popping up where it can. And I think Brandon Puckett is on the call, or he was on the call, but we saw this happen in North Carolina after, oh my gosh, Hurricane Florence. Essentially what happened was, with enough wind, the Spartina, as it waves back and forth, almost cuts itself off when it rubs against a nearby oyster. So it's entirely possible that could happen as well. But that is more of, again, how important extreme situations are versus kind of the everyday. It does seem in the everyday, the clumps may even be stabilizing the shoreline more. So that is yet another study. I could have 2 more PhDs off of this. But yeah, again, hopefully paving the way for it is complicated, I'm sorry. Everything is very context specific, and yeah, high wind or a high wave event, it's completely different than ambient conditions. So.
Well, we're almost up against the hour, so I want to go ahead and stop us and respect everyone's time. But I very much appreciate this is one of our best attended webinars, and our questions have gone right up to the end of the hour. So thank you, Emory, and thank you everyone for being engaged in this talk. Our next webinar will be February 19th, and Drs. Aaron Pilnick and Don Berenger are going to talk about sponge restoration. So I hope I will see a bunch of you back for that webinar, and we'll have some great conversation about that topic as well. Thanks again, Emory, and thanks everyone for coming.
Thanks, everyone.